Hello everybody, welcome to the first session of our CosmoVerse lectures at your desk. In our first session, our first speaker is going to be Dr. Tamara Davis. Dr. Tamara Davis describes herself as an enthusiastic professor at the of astrophysics at the University of Queensland. Among her efforts in cosmology, we mention her role as a leader of the Australian Dark Energy Survey and as Deputy Director of the ARC, Center of Excellence for Gravitational Wave Discovery. She also ran cosmological analysis for 3 different supernova cosmology teams, including ESSENCE, SESS, DES. And during the 2010s, she also worked with the Wiggles survey doing baryon acoustic oscillation cosmology, and is continuing to do so now with DESI. Among the prizes that she received in recognition of her commitment to our field are the American Institute of Physics Science Communication Award, which she won as a communicator of science and occasional guest of astrophysics documentaries, including the episode of Black Hole Hunters. Finally, she was awarded an Order of Australia for her significant service to astrophysical science, education, and to young astronomers, a commitment that she's also showing to us now, as she will be talking about the nuts and bolts of supernova cosmology. So please, Dr. Davis, feel free to start, and thank you again for joining us today.
Excellent. Thank you so much for having me. Thanks for that very, very kind introduction. I love doing some supernova cosmology in general, basically trying to figure out the universe from whatever direction one can possibly figure it out from, whatever data is available. But I've done a lot of my research has involved supernova cosmology in some way or another. You often hear supernova cosmology. We have the supernovae. We know how bright they are intrinsically, and therefore we can figure out how far they are away. Combine that with some redshifts, we have a Hubble diagram, and voila, we can do cosmology. Today, I'm going to go into a little bit more detail. I've been asked to tell you a bit about how you actually make the Hubble diagram and how you use that to then derive cosmology in just a little bit more detail. So I'm going to use the Dark Energy Survey as a case study, since it's the most recent big supernova compilation that's come out. And I'll start from the very basics and step through. So I know we're having a question session at the end, but if you'd like to ask questions along the way, I'll try and keep an eye out on the chat or raise a hand or something, and I'll make an attempt to respond during the talk, because I don't like going on forever about something that people have lost track of. So please just disturb me if you want to ask questions. Okay, this is a Hubble diagram. This is how bright a supernova is on the vertical axis. Here's a beautiful galaxy with a before and after photo where you can see the little supernova, and you get these light curves that brighten and fade over the course of a month or so. And we usually try and measure them these days in many colors, so we can do color corrections and understand dust. That makes the vertical axis of one of these Hubble diagrams, and on the horizontal axis you have a redshift. Now for the redshift, you typically want the redshift of the host galaxy, not the redshift of the supernova, because the supernova has outflows, like its photosphere is moving towards us, it gets blue shifted lines, and also it's really hot and the lines are really wide, so it's hard to get precise redshifts from it. So ideally you want redshifts from the host galaxy. Put those together and voila, you have your Hubble diagram. Now, of course, the voila is a little bit of work and effort. So let's talk you through a little bit of that in some more detail. So how we go from a Hubble diagram to understanding cosmology is thanks to the fact that how bright something appears is dependent on the cosmology that governs the expansion of the universe. So here, the distance modulus, which is the difference between the apparent magnitude and the absolute magnitude of an object, is related to how far it is away. So this is the luminosity distance, and the luminosity distance is dependent on the cosmology. So here Ez is the Hubble parameter as a function of Z as a function of redshift divided by H0. And you can see in various different cosmological models, it has different functional forms. And we can measure the matter density and other things like the cosmological constant density or the equation of state of dark energy by looking at how this magnitude changes with redshift. Observationally, we measure the distance modulus of supernovae, but it's not true that they are standard candles, even though we say that often. Really, they're standardizable candles in that if you apply a bunch of corrections to the observed magnitudes, you can get something that's a very consistent magnitude. So they're some of the best standard candles we have, but there is still intrinsic diversity in them, even after we've made all of these corrections. And this is the sort of basic formula that we now use with all of the corrections. So what these are is each supernova has a certain magnitude, so that's related to its peak brightness, a certain width of its light curve, so how long it takes to rise and fade, so how long it takes to explode, a certain color, which is related both to the intrinsic color of the supernova and to any dust extinction in the way. It has a certain host mass, so that's the mass of the host galaxy, and we see a systematic difference between the brightnesses of supernovae and high and low mass hosts, which might relate to the progenitor pathways. And we then also have the issue in our surveys that we're rarely ever complete in that we have selection effects. Every astronomical survey has some sort of selection effects, and so we have to take into account that. So those are different for every individual supernova, and then when calculating the distance modulus to compare with theory, there's the population parameters which tell us sort of a theoretical form of how the stretch relates to the magnitude, how the color relates to the magnitude, how the host gas relates to the magnitude. So these are parameters that will be a single number for a particular survey that has a variety of different supernovae. And when you do that, you take something where you have potentially more than an order of magnitude in scatter in the peak brightness and get a much smaller magnitude. So here's just a little example of sort of a view in of the peak of a light curve before and after the first two corrections of this term. And Anais grabbed some data and made that for us. Any questions so far? If not, I'll dive into just quickly how we in the dark energy survey measured these. So first you have to find the supernovae, and we use the dark energy camera over in Chile, took many images of the same patches of sky and looked for things that change. So it was a big survey. Many people were involved, did lots of different things. Here's a bunch of people who were involved in the supernova part of it, and thanks to all of them for some of the data that I'm going to be showing today. Now, with the dark energy camera, we took light curves of the supernovae, but we also need to get spectra to get the redshifts. And this is the 2DF instrument on the Anglo-Australian telescope. It's a fiber-fed spectrograph with 400 optical fibers. And this is what we used to go and look for the redshifts of the objects after we had discovered the supernovae. And it was very convenient that the field of view of DECCAM and the field of view of 2DF are almost identical, so it made for very efficient follow-up. Note though that we've got 400 optical fibers, and we put about 100 of them-ish on a supernovae hosts in any observation, which means we weren't capturing the supernova while it was live all the time. We were looking at the supernova after it had faded and looking at the host galaxy, which, as I said before, it has the most precise spectral lines anyway, so that's what is ideal for measuring the redshift. And Chris Lidman I wanted to give a shout out to because he was the heart and soul of OzDes, especially in the early years before I took over. So this is the field of view that Des surveyed for weak lensing and other parts of the survey. But for the supernova part, we just looked at these little lines of sight. So we just got 10 patches in 4 groups and repeatedly observed those on about a weekly cadence. And at the end, you get a result like this. So here are those 4 groups of fields that we looked at. The orange dots are galaxies and the sparkles are supernovae. So one thing that you can see from this is that there are patches of time when we were observing and patches of the time when we weren't. And so you have, that's the seasonal gaps when our fields went behind the sun, essentially. So how do we go from these measurements to Hubble diagram? So this is one of my favorite plots that I have ever made for a paper. This is about the 1500-ish supernova light curves and the models for their light curves that we took with DES. And I love plotting the data in its sort of rawest form because you see things that you might not obviously notice. Firstly, we measured in 4 different pass bands, G, R, I, and Z. And you'll notice that as you go up, so these are vertically offset by redshift. And you can see that as we go up in redshift, the supernovae become too faint in the bluer wavelengths to be detected. So that's why there's no light curves in this sort of green filter up above a redshift of about 0.35-ish. And similarly, they disappear from the red filter after they go about 0.85-ish. And so that's why when we did our cosmology analysis, we did a cut at redshift of 0.85 and saw what happened with only the supernovae that have 3 filter color information. So this is sort of a more scientific plot of the same thing, where here's a supernova at redshift of 0.155, where you can see G, R, and I light curves, and again at a bit higher redshift, and then something at redshift about 0.8. And you see we have different bands at different redshifts. And this is sort of important because remember we said we want to measure the peak brightness of a supernova? Well, what do we mean by the peak brightness? Originally, we often define it as the peak, how bright it got in B band. But as we've gone on, that's not been the most useful peak brightness to use. So we now use something called MX, which is sort of a bit of an arbitrary band in between. And you also notice that we don't actually have observations often at the peak. So we don't actually time our measurements perfectly so that we always get supernovae at peak. So we have to have a model light curve that we fit to figure out what the peak magnitude might be. And K corrections come into play. If people had videos on, I would say put your hands up if you know about K corrections and how annoying they are. But basically, we have fixed filters, and as the supernova gets redshifted through these filters, different parts of the spectrum will be being in the different filters. So here's an old plot. I think I've got, yeah, this was from the Paravolopoulos paper in 2007, but I think it might have been an earlier paper from Alex Kim, I'm not sure. I tried to find the original reference. But anyway, you've got a supernova spectrum in the background and the filters in the foreground. And you can see that a supernova at a redshift of about 0.45, you're sampling approximately the same section of spectrum in the red filter that you do in a blue filter at redshift 0. So if you compare a brightness in red filter at redshift 0.45 and a blue filter at redshift 0, you get approximately the same sample of the supernova, and that would be your best comparison on a one-to-one basis of how bright they are. But of course, what happens if you have a supernova at redshift 0.2? It's halfway between the filters. So you have to have a model to analyze that, and that's one of the things that is done by the SALT-3 model, where we model the supernova light curves. So you'll also notice that the supernovae are different shapes in different colors. And that's because cool stuff happens when you have explosions like a supernova. This is a plot that Stefan Blondin made, where you can hopefully see the animation of, as time goes on in the light curve, it starts very blue with a peak at low wavelengths in the spectrum and becomes red over time. And so this means that the supernovae start blue and end up more red. And that has to be taken into account. But also that's some of the things that can help us identify a type 1a supernova. This extra peak that you get in red wavelengths, for example. Now, incidentally, I just wanted to mention one of the fun things that we got to do with the DES survey, which was measure time dilation in the distant universe for the most precise measurement that had ever been made. And here you can see these, here in the rest frame epoch here, I've divided by 1 plus z, which is the expected time dilation due to the expansion of the universe, because these galaxies are moving fast away from us and they're further. And if you compare how wide supernovae are in the same band, where the same part of the spectrum is being measured, if I take out the time dilation I'm about to do in the next plot, you can see that the high redshift supernovae are much wider than the nearby ones. And so my student Ryan White measured and quantified this, and basically without any light curve modeling, just like compared the width of light curves at different redshifts and plotted how much time dilation you need to make the light curves wider. And the black dotted line is the predicted 1+Z factor, and the blue dashed line is the best fit. And if you can't see the black dotted line, that's because it's smack bang under the blue dashed line. It's I was really excited to see this measurement. It's a really nice measurement of time dilation. But anyway, I digress. So more details about how to get the supernova. Let's go take yet another step back and talk about getting the data themselves. So there's a variety of different steps that you have to do. And over the basically decade where we ran DES, there was over 50 papers that validated our supernova data and techniques. So it was a lot of work, and I'll try and explain a little bit why. So here's a few of the different things, like actually just taking the data, simulating a sample, classifying the type 1As, and doing modeling of dust and things. So firstly, how do you measure the brightness of this supernova when it's hosted in a galaxy? Previously, people might have done difference imaging, where you take a before and after image and compare the difference. But as you can see in this little animation, the seeing how good the observation conditions are on any particular night or stuff can change the images quite dramatically. And so what we did was forward model the entire galaxy and the supernova in it to measure the most precise model possible. So we didn't just do difference imaging. And this was very computationally intensive. This was one of the more difficult parts of getting accurate photometry. But we got calibration to 5 millimag, which is better than had ever been done before. To do that, we also did things like checking the differential chromatic refraction. Different colors get bent by different amounts through the atmosphere. And so they'll appear on different pixels in your image in different colors. And we had to take that into account. It's like you can't just put a circle over your star and it's going to be the same in all different colors. You had to take that into account. Not only that, the size of the blob, the seeing, depends on the color. And so that was all taken into account for some of the first times here with this data. And I'm giving you some of the researchers who did this work in the pictures on the side. The light curve model is really important, and SALT 3 is sort of an updated version of that many people have worked on over years, SALT 3 being the latest version of it. And this training on a really large wavelength range is really important for this, and that was we had a bigger data set over a larger wavelength range than had been done before. So that was made the model of how the supernovae brighten and fade and how we take into account K corrections and all that sort of stuff much more robust. And then lastly, you also have to look at the host galaxies, because I said we use host galaxy spectra in order to get the redshifts. And what if it's not the right host? So you can see here's an example where we've got an image with 3 big galaxies and a supernova where the red cross is. Now, which of those galaxies hosted this supernova is not necessarily obvious. So people like Helen went through and looked in great detail about how often we would get mismatches and how much that would impact our results, and made sure that it was a very subdominant effect. So these are just some of the details that went into generating the data. And then when you do some of the analysis, one of the things that is important is to simulate your data set really well so that you understand what the selection effects are that are going into this. And Maria Vincenzi led some of the simulations here. And we're able to say from first principles basically what the distribution of supernovae will look like. So the black points here, which are the data, and the gray histograms aren't actually fit to one another. The simulation is based on other information that we knew about the population of supernovae and about our survey. And it just so happens that they match because we understood our survey really well. So we think that's a really big improvement on what has been done before. I see there's a question.
Yes. I wanted to ask regarding the identification of the host galaxy for the supernovae. I noticed in the Pantheon Plus, there's some hostless supernovae. Do you have any supernovae which are which you couldn't associate with the host galaxy? And if so, how did you deal with them?
We didn't in this case because we required that all of our supernovae have host spectra, because we wanted to have the most precise redshifts possible. So yes, we required all of ours to have hosts.
And do you know? Sorry, go ahead.
No, you go.
I was just going to ask, like, how do you know how people deal with hostless supernovae? Like, how would they get a redshift in that case?
So you can get a spectrum and a redshift from the supernova itself,
Yeah.
and that has been done in the past. And the ones that appear in Pantheon and previous surveys were using the spectrum of the supernova itself. That's fine. Like you just have a bigger error bar,
Yeah.
and is the potential for biases because you do tend to get systematically blue shifted supernovae because you're seeing the part of the supernova that's moving towards you. So you've got to be slightly careful about that. But that's not a massive effect, and yeah, it's probably negligible difference. And so it just has slightly bigger error bars on the redshift, but
But redshifters are typically subdominant anyway, right? So.
Yeah, exactly. The magnitudes are the bigger errors
Yeah.
anyway, so it's not a big deal.
Okay, thanks.
Cool. Great. Keep the questions coming if anyone has any more. The last thing in terms of like doing the analysis that I'll mention is modeling dust and modeling color. So as I said, there's some intrinsic variation in the supernovae. They're not all the exact same color. This can have something to do with the progenitors and how the formation mechanisms, but also to do with dust and obscuration, which is really important if you're using color, etc., to measure or if you're measuring how bright something is. If there's any obscuration, it's important to take that into account. And this remains to this day one of the most difficult parts of supernova cosmology, and is the part that leaves the biggest error bar. We put our uncertainties in here. We try and deal with systematics throughout the analysis by looking at how badly wrong we could possibly be, and including that in our error bars. So we have covariance matrices that take this into account, and I'll get into that in a little bit more detail later. For DES and for many future surveys like LSST that's being planned, we won't have spectra of the supernovae, and spectra of the supernovae is what was traditionally used to classify the type 1As by, for example, looking at the silicon feature, and there's some distinctive features in the spectra. But it turns out that if you have light curves in 4 colors, it's really not that much else that looks like a type 1A supernova. And even just by taking the ones that pass the salt fits, you already have a pretty pure sample. But in addition to that, we did machine learning to trained machine learning to figure out which of our light curves were real, genuine type 1A supernovae. And we used 3 different classification algorithms, and we trained them on 7 different variants of what the population could look like. So they weren't just being trained on the same thing that they were then being tested on. So the classifiers work really remarkably well. And you can see in this little plot at the bottom a fit where you have a simulation and a with and without contamination, and you really can't see the difference very much. They're very, very similar. The contamination is a real small effect. So we thought at the beginning of DES that this classification might be a problem, but really it turns out to be one of the smallest systematics that we have. And this is what the difference in the different classifiers looks like done on real data. And again, the classifiers all agree very, very well. Okay, so let's have a look at some of the data then. And this is something that you can play with yourself. Oh, sorry, another question.
Yeah, I just want to ask, like, does that mean in the DES catalog there's like a sort of a classification of whether each supernova is likely to have been a 1A and how probable that is?
Yeah, correct. I'll show you the files in a few slides, and I'll show you which things to look for.
Thanks.
Cool. So I thought it would be fun to have a look at what the data looks like before and after making these corrections. And so, actually, the answer to your question is coming up in the next slide, basically. So here is the data release, and previous data releases look somewhat similar to this, but here's the DES stuff. You can download this, it's all public, and we have code that you can use to run this from start to finish if you want. So there's the data file, there's all the simulations that were done, there's the model, which is like what the light curve model looks like, there's the classification code, there's this part is what most people will need, which is the distances, so it's like distance moduli versus redshift. And then there's the chains after we'd done cosmology fitting, and some of the corrections that we did for that differential chromatic refraction, and the Pippin files. Pippin is the pipeline, and so the Pippin files is the thing that you need to go in and then run this from start to finish, and then tweak whatever parameters you want to tweak and test out things on your own. So this is all here on GitHub and on Zenodo. And I was going to have a quick look at what's in this distances covmat file. So first, having a look in here, what you'll see is there's a Hubble diagram. So this is basically everything you need to fit cosmology is in here, plus the systematic and statistical covariance matrix. So these are how all of the different data points are correlated. These are the only two files you need to fit cosmology. If you want to get a bit more detail and a bit more excitement, you can go and look at the metadata stuff, and that has all of the additional details, like things like what's the probability of being a type 1a, what the host galaxy mass was, etc., etc. And you can go and see all the details there. And there's also a statistical only matrix, which is the covariance matrix minus some of the details. And in fact, this is basically empty because the statistical is the diagonal in the and that's actually held in the DES Supernova 5-year Hubble diagram. There's a mu error term, and that has to be added to the diagonal of the covariance matrix before you do your analysis. And that's a trap for the beginners that sometimes gets missed. If your error bars look excessively small, it's probably because you've forgotten to add the mu error term to your covariance matrix. Yep.
So I was just wondering if you wanted to do the trip corrections yourself, do you have the uncertainties on the stretch, color, and flux and the covariances between them for each supernova? Is that in there as well?
So yes, so I'll step you through that in just a second.
Okay.
Yeah, good question. So this is what the basic Hubble diagram looks like. So here you've just got the idea of the supernova, the survey it came from, and the main details. You'll notice that the last one is the uncertainty in distance modulus, and some of them have ginormous uncertainties. And that means that if they have ginormous uncertainties, that means they have a very low probability of being a type 1a. And so they basically contribute nothing to the cosmology fit. And of the 1824-ish, I think that we had about 150 will have very high likelihoods. So that's always why we said about 1500 DES supernovae and that kind of thing. So this is basically all you need. It shows you how to construct the distance modulus from the pieces as well. And this, which is possibly too small to see on your screen, is the more detailed file with the metadata. So here you can see that it's got all the redshifts and the peculiar velocity information, and I'll explain a bit more about those in a minute as well. It's got all the host galaxy properties, not only the mass, but also where it is on the sky, how far the supernova is away from the center, like the angular separation from the center of the galaxy, and those kind of things. All of those things that you were just asking about. So the supernova properties, it's got the peak, the color, or the stretch, the color, all the errors on these, and the covariance between them. So this is all here for you to play with as much as you like. It's got the probability of being a type 1a from all of the different classifiers and sort of the combined one that we ended up using, or the final one we ended up using, and the distance moduli and the bias corrections due to incompleteness and other things in there. So hopefully all of the information that you could ever possibly want is in one of these files. So this is what the Hubble diagram looks like when you don't do those corrections. So here I just made these yesterday, so sorry if they're a little rough, but this is if you just make the first correction. And minus 2.5 log 10 x naught. X naught, this is basically the magnitude, just the plane magnitude measured for where the peak is before doing any corrections. Now, in the file, in the GitHub, there's also all the global parameters that you have to apply, the alpha, beta, gamma, and the absolute magnitude that's used there. And these are fit on the analysis of the entire Hubble diagram. So here's what it looks like before you do any corrections. Here's what it looks like after you've just corrected for the stretch. So I'll flick back and forth between them a couple of times. Then this is what it looks like after you've corrected for color as well. And then for the host match, and you can see it just sort of shifts, some of them shift up and some of them shift down in a host mass because it's a binary difference, either it's a heavy or a light one here. And then you add the bias correction in the end, which is a 4D correction that's done in not just in magnitude or in redshift, in bins of redshift, but in bins of color, etc. And so this is how I'm just going to flick between the original uncalibrated supernovae and the final calibrated ones. And you can see the relationship is quite a bit tighter when we do that. And so this is a bit of how the Hubble diagram is all put together. I got a bit carried away and then I started playing with different things. And this is the same thing. I've now put a relative to the model plot down the bottom, but this time I've colored the points by the next correction that's going to occur. So this is the uncorrected version colored by stretch. And then here, this is the one that has been calibrated to stretch and it's colored by color. So you can see that there's a gradient here that's going to become better in the next plot. And then this is by host mass and by bias, and then to the final plot. So that was just a bit of fun showing you why we do that. We can actually reduce the scatter quite a bit in this Hubble diagram by using these this calibration. Okay. Any questions before I go on to the cosmology part? If not, diving straight in. Okay, so we've already talked about this cosmology side here. I just wanted to give you a tiny little bit more detail. And here, the luminosity distance, as I said, is dependent on the cosmological parameters. Also important to note that it's divided by megaparsecs. If you've got 25 out the right, that means it's in the units of megaparsecs, and that's otherwise not dimensionally consistent. When we do the luminosity distance, we use 2 different redshifts. That's because when you calculate luminosity distance using this integral down the bottom here, you want this to be the cosmological redshift. But the reason luminosity distance differs from co-moving distance is that you get the beaming and the time dilation effects, which actually depend on the observed redshift, not the cosmological one. And measurements are getting precise enough that this is starting to make a difference. So you put your observed redshift in the front here, not your cosmological one. So yeah, and then of course, in my previous measurement or previous thing, I neglected curvature. This is what it would look like with curvature, where you have a sign or a shine in here. Okay, so I mentioned redshifts and which redshift to use. In the files that are generally provided for supernova cosmologies, there's 3 different redshifts. First one is the redshift in the heliocentric frame. That's the redshift we measure from our sun or our Earth. And that's basically the redshift that you get from the telescope. The next redshift is the CMB frame redshift. So this is when we trust that Julian and others have done the measurement of the dipole in the CMB really well, and that's purely kinematic. And we correct for our Earth's motion with respect to the CMB to get the redshift in the CMB frame. So our observed redshift in the CMB frame. And then we do one final correction, which is where we take a model for the peculiar velocities around us and correct for those as well. So now we try and remove the motion of the host galaxy that's hosted the supernova. And this is a bit uncertain because we need a model of the velocities of galaxies, and that's not known perfectly. But this does reduce the scatter, excuse me, compared to not doing this. And you can see the effect here. This was actually for DES. We don't have this. All basically makes a big difference at low redshift, not high redshift. So it matters more for the wide field low redshift sample. And this was the plots from Pantheon Plus, where in this bottom right plot, this is the difference between the observed mu and the expected mu. If you calculate your expected mu using the heliocentric redshift. And you can see that there's a bright spot in the top right and a dark spot in the bottom left. And the circle and cross are the dipole of directions of the CMB. And so you can see that we do indeed see a dipole in the supernova data that it corresponds approximately here to what the CMB direction is. When we subtract the CMB dipole and go to ZCMB, you see an interesting effect. The dipole now looks like it's going in the opposite direction. So you can see that there's a bright patch in the opposite direction. And what has happened here is that we have overcorrected for the velocity relative to nearby supernovae, because the nearby supernovae do share some of our motion with respect to the CMB. So we shouldn't actually subtract the CMB velocity from them because they're moving with the CMB with us. So we've put a false dipole on those nearby supernovae. So by correcting for the model of the motions of nearby supernovae, we can reduce some of that. We don't get rid of it completely because our model's not perfect. But if our model of peculiar velocities was perfect, we would expect this top map to then be just sort of plain green, having corrected for peculiar velocities. So this shows that you can see that it's doing something right. It's getting less dipole by doing this, but the peculiar velocity model isn't perfect yet. And of course, there could be, we don't actually expect a dipole to ever explain all of what's going on, and there could be other interesting physics going on by looking at this as well. Okay, so I've been talking for a while, and there's a bit more to get through in terms of getting to cosmology. So we have we supply the statistical and systematic covariance matrix. The systematic covariance matrix I'll get to last, I guess, and explain how we derive that. But basically, in order to compare to cosmology, this top version is the simple chi-squared that hopefully everybody knows and loves, where you have some measurement here for each I is each supernova, and you have a model prediction for how what the distance modulus should be. And that model might be W0 WA CDM, it might be lambda CDM, all with different parameters like matter densities, and divided by the error bar. Now, because our points are correlated, you do that as a covariance matrix, not as a simple sum like this. And so this would be the term that you use. Importantly, when we do this, for all of the high redshift cosmology stuff, we marginalize over absolute magnitude and over H0. These two are combined parameters, and I'll explain why here, because you see the luminosity distance here has sort of three terms, so 1 plus z, a c on H0, and the integral. So you can separate them out, and when they go into the log here to get the distance modulus, and they become a sum when you separate them out. And you can see this 5 log c on H0 is just an additive term in our distance modulus. Now, that means it's a constant offset. So the effect of H0 on a supernova Hubble diagram is simply to shift up and down the distance modulus. It's just a constant offset. It doesn't change the slope or the shape at all. Whereas all of your cosmology, from matter densities and dark energies and weird equations of state, that all changes the slope, the shape of the curve. So and H0, you can see in the observed version, the absolute magnitude is also a constant offset. So H0 and absolute magnitude are completely degenerate, which is why low redshift supernova surveys are used to measure H0 when you calibrate the absolute magnitude. But you don't need to calibrate the absolute magnitude to get all of the information on the high redshift stuff that you want to do for matter density, etc. So usually we just marginalize over a combination of H0 and absolute magnitude, throw that information in the bin, get no constraint on H0 at all, and just use the shape of the curve to measure the parameters we're interested in for cosmology. So this little M script, if you see MSCR, that usually means M script. It means that we're marginalizing over this term here. So there's a cool way to do that. You can do it analytically, so you don't have to loop over anything. And this is the equations that you need. I stole this from this screenshot from Ryan Camilleri's paper where he looked at exotic cosmological models with DES. But this is, if you chuck in these equations in addition to your chi, or your chi-squared, then you don't have to worry about absolute magnitude. It's all dealt with, and you can go home happy. So what is marginalization actually doing? It's just summing over the terms that you don't want. So you have your contours, you project them over the term that you don't want. And here is just, I thought I'd plot quickly what the difference looks like for, say, a delta H0 of -5 kilometers per second I've got here. And you can see the red points are offset by a delta H0 here. And for dark energy, we don't care about this at all. All we care about is the shape of the curve. And so this mu on the vertical axis, sometimes you'll see it as a number that's like 18, like, 12 to 19. Here it's a number that's like 34 to 44. And the actual number on this axis matters not at all. It's all the slope and how the slope changes with redshift that has most of the cosmological information for dark energy. Okay. Oh, I chucked this in because often you see the Hubble diagrams like this with log redshift, but anyway, that's not important. So yeah, summary. If you want to do H0 measurements, you need to calibrate your supernovae, and usually that's only relevant at low redshift. If you want to measure different cosmological parameters, typically you need to measure a wide range of redshifts and look at how the slope changes as a function of redshift. And that gives you your interesting shaped contours. Okay, so the final thing to note is that in all of these, the systematic control is really key. If you look at previous supernova surveys, including the DES survey from 2019, which was just a spectroscopically selected sample of a couple of hundred supernovae, these were generally estimated that the systematic errors were larger than the statistical ones or about equal. And so this is a real challenge because obviously you don't get any better by adding more supernovae unless you can beat down the systematic errors somehow. So that was like DES was designed from the ground up to get really, really good calibration to get rid of that systematic error as much as possible. And all of the effort to improve the data was so the systematics could be lowered. And it turns out that once you have more supernovae, you have more information about how supernovae behave. And that means you can actually understand the populations better and constrain dust and things better, and you can actually improve things. So it's not a zero-sum game. You haven't just hit a systematic flaw with any of these. It's just that the data wasn't good enough yet, and we didn't have enough supernovae to understand supernovae well enough. So that's been improved here. So here is the systematic error budget, where the gray bands here is what we had for DES in 2019 when we just had a couple of hundred. Now with almost a couple of thousand, the systematic error bar has gotten much smaller, and the statistical has also reduced, but the systematic error bar is still half the size of the statistical one, which is a big achievement. So you can see here, this is from Maria Vincenzi. She makes some really cool plots. These different colors are telling you what the different things is. So the purple, which is a tiny contribution, is how much systematic error we get from supernova classification. Oh, by the way, I should say how we calculate these systematic errors is that we take what we think the worst possible calibration we could have done for our filters. We put that onto our into our data and run the entire analysis from start to finish with that error, and you look at how much things change between that and the original one we thought. And that goes into our covariance matrix. And we do this for every systematic that we could possibly think of, from everything from redshift errors to extinction corrections to calibration, and put that all in and add it all up together to figure out where the modeling choices could have, how big an impact they could have had. And so, yeah, so here you can see that the intrinsic supernova 1A properties, or the dust, so this is like color terms, they make the biggest systematic uncertainty. So that's where sort of the model choices matter the most. You can see light curve modeling and calibration have some effect in here. They're the second sort of most dominant one. Then peculiar velocities and redshifts, not so much. Extinction corrections for Milky Way, at least, not so much. And survey modeling is pretty small. So here's it broken down a little bit more. We called these sock diagrams. We considered getting socks made that would match this pattern. But the key takeaway is that we were able to improve and control systematics, we think, quite well. And the smaller systematic ended up being classification, so that was no longer a worry. But the top systematics is the supernova dust properties and the calibration, and sort of the model there. One last thing I wanted to mention, I called these George effects. This is George Astafyew made a paper because he noticed that there was a shift of 0.042 magnitudes between some of the supernovae that were in common between DES and Pantheon Plus, and noted that if you that Pantheon Plus was slightly closer towards lambda CDM and not time varying dark energy, and so thought that maybe that was to be preferred, which we try and avoid that kind of confirmation bias by trying to judge data by which model, by the fact that it fits our best model. But Maria led a response to this paper because this got a lot of attention, so we thought it was worth answering. And we know exactly why those differ. So this is a really interesting point, sort of an important point. If you have, when we do that bias correction that I showed before, that's what sort of a lot of this correction comes from. And that's because the dark energy survey is much more complete than Pantheon Plus. And we don't have to correct the magnitudes of the supernovae so much for the supernovae that are not in our sample. So this is what we've tried to show up the top in these sort of cartoons, is that the DES supernovae that appear in Pantheon miss a lot of the faint supernovae because they weren't in that sample, because that was a spectroscopically confirmed sample, and that has much worse selection effects and wasn't as deep as the final sample that we put out. So the fact that we didn't have to correct supernovae for the supernovae that were missing accounts for a bunch of the difference between these supernovae. The other differences were that there was improved intrinsic scatter model, the fact that we had 4 colors out to high redshift, and also the deeper imaging in the dark energy survey gives us better host masses. So we managed to get all of that extra information in, which all shifted some of these supernovae and made a little bit of difference in their magnitude. So if you don't expect the same supernova to have exactly the same magnitude in different surveys, 1, because here we did improved analysis techniques, and 2, because there's bias corrections that are going to be different for every survey. And besides, if you look at, there's been a bunch of discussion about the sort of different supernova surveys and the fact that they give slightly different answers, but that is completely expected in your analysis, because you can see here, I mean, they all overlap at 1 sigma. So this is a plot of W0 WA put out by the DESI collaboration when you fit with DSE, BAO, CMB, and 3 different supernova compilations. And it doesn't matter if you include BAO and CMB or not. Actually, I should have used one of the plots that doesn't include those, but they all overlap at the 1 sigma level and are all very consistent. Okay, so I'll stop there and I'll see if there's any immediate questions. But we also wanted to make this a bit interactive for you. And although I didn't manage to make it interactive now and get you to do something, there is a tutorial that I've put together that I've used for students in the past here at UQ. And this basically gets you to step through calculating the cosmology from the Hubble diagram. And so it has all the instructions you need, all the theory you need, and some example code to get you started. And so this is a sort of a bit of a fun exercise, and I'm happy if anyone else is teaching as well that they can use this project if they like. So you can jump in and do that. And the other thing that you can do is go to the Read the Docs for DES, where we have a bunch of example code that you can use to do your own analyses as well. And so I'll leave it at that. Thanks very much.